Have fun. Hello and welcome back to Calculus 1, section 2.5 on limits at infinity. So to contrast this to the previous lecture, infinite limits, we are now looking at the limit as x goes to positive or negative infinity of a function, looking for an answer that could be either finite value L, one of the infinities, or obviously does not exist. So you can have any of these situations, and the key for this is there. So this is limits at infinity. So you are looking far out. You're looking far out, and you are trying to figure out what is happening as the function goes to infinity in x direction, either positive or negative. So to illustrate all three of these ideas, we can start by, let's say, looking at your favorite function, e to the negative x. So that's a good one. Y equals e to the negative x. That is the decay function, decay graph. There we go. And what is happening as the limit of x goes to infinity of e to the negative x? So where is the y value going as x goes to positive infinity? Zero, exactly. So as you are going to positive infinity, which is going this way, you see that the y value, if you picture a point that it's moving and going to x infinity, positive infinity, you see that the y value keeps dropping, and is dropping down to 0. So as it goes to positive infinity, we have an answer of 0. And that would be this graph over here, the first line, where you get a finite value as the answer. Another good example that you guys are going to run into and need to know is the graph of inverse tangent of a function. So you have your f of x of tangent inverse of x. Now, a lot of people don't know the graph, and you should, because this is going to pop up, especially in Calc 2 and differential equations, if you're going there. So here is the graph for inverse tangent. Draw two asymptotes this way, equally distant. Label those as negative pi over 2 and pi over 2. And then snake the function through like a sideways tangent, like this. So this is your tangent inverse of x. Some of you might have learned these inverse trigonometric functions as arctangent. So this also can be called arctangent of x. And some places even go with the atan x. All of this means the same thing. Here at the school, we use this notation because all of the books we use that notation, but I learned it as this, and then throughout the years saw the third one. So all of this means the same thing, inverse tangent, okay? Inverse tangent, all of them. And now I can ask what is the limit as x goes to infinity for inverse tangent of x? And you will say what? Pi over 2. Very good. From below, right? So as you are going on x to positive infinity, you see that the y value for each point that it's going towards positive infinity, each point y values are slowly creeping up to pi over 2. So these two examples show the first case where you are looking at a finite number to be your your answer for the limit at infinity. But now, you might want to look at, let's say, limit as x goes to infinity of x squared, right? And if you look at the graph for x squared, what happens as x goes to positive infinity in this graph? It goes to positive infinity. Very good. Because this will go to positive infinity. So the answer now is also infinity. Another example of this would be e to the x, let's say. So what is the limit of e to the x as x goes to infinity? And we know that e to the x will shoot up like that, and you have positive infinity again, right? Because it goes up. Now that satisfies the second possibility, where you have limit at infinity could give you also infinities. And the last one is, well, here you go, so you're happy. Let's consider sine x as a function. So y equals sine x. You can do cos. You can do any trig function. All of them fit in this scenario. What is the limit of sine x as x goes to infinity? Well, if you consider your sine x, and sine x is a wave, it's going to do this forever, right? And it does down on the negative side as well. You have one big fat does not exist in this case, because there are infinitely many points between -1 and 1, which is the range, the y values of sine. And going to infinity, it's all of those points at the same time. So since sine, cosine, they all oscillate, the answer is the limit does not exist, fitting that third spot, right, of the NE. So when you are dealing with limits at infinity, you can have finite value to be the answer. That will be the first two examples. You can have the infinity, whether it's positive or negative, depending on the function. Second two examples. And the third example, we can use all 6 of trig functions for that one, is that the limit at infinity does not exist because it just oscillates like this. You can't really have a finite value, and it doesn't shoot to infinity because it's definitely bounded between -1 and 1 in this case. So those are the situations that you can run into. And now we would like to know the use for this, so that we can eventually, push this into physics and then eventually into engineering, so we can build stuff. So the first use of this would be horizontal asymptote. And horizontal asymptote. Now, you did have this in your pre-calculus course, and you had this for a single type of a function. It was a rational function. I even know it's 2.6 section in your pre-calc course. Only rational function when you divide a polynomial by another polynomial. That was the only place where you dealt with horizontal asymptote, and you were forced to memorize the rule. Does anyone remember those 3 rules? Yeah? Yes, that's one of the 3. Good. If powers are the same, right? If you have x squared on top and x squared on the bottom, then you take the front coefficients, you divide them. Good. There are 2 more.
Something with the square root?
No. That's something else. Okay, so you don't remember. Good. Because we don't need it. We are going to do the limit definition for this thing, so you really don't need that one anymore. Right? Got you scared there. Even though, good thing you remembered at least one way to make me proud, right? I mean, you didn't take my class, but still, right? You did take someone's class, so maybe we'll track down that person, pat on the back. Your student remembers one thing. It's good. Anyway, so horizontal asymptote is going to be horizontal line that the function approaches as it goes to infinity. The difference between horizontal and vertical asymptotes is, the difference is you can pierce through horizontal asymptotes. So if there is a horizontal asymptote at, let's say, y equals 0, the function can cut through locally. It has to obey and follow horizontal asymptote only at infinity. So as the function goes to infinity, it has to bend and follow horizontal asymptote. But anywhere in between infinities, so for non-infinity locations, so if you come up with x equals 1,000,000 or x equals to -10, function can actually cut through the horizontal asymptote. While the vertical asymptotes cannot be pierced anywhere ever. So that's the huge difference between these two lines. So now, let's go.
Professor,
Student.
what is the only exemption? Unless it's something infinity, you said?
There are no exemptions. It's just that functions have to follow horizontal asymptote at infinity, but they could cut if they need to cut through at any other location they can. No exceptions. You're confusing that with English when there is exception. You know how there is a deer, there are no deers, and sheeps, right? And then there's news, but there's no new. It's a single piece of new. So that's the exceptions, right? In math, no exceptions, ever. Which is why I do this. It's cheap and easy. You learn one rule applies everywhere, right? Anyway, horizontal asymptote. So let's go. Definition, theorem, whatever. Definition, I guess. So, horizontal asymptote of f of x. Yes, I remembered it. So, horizontal asymptote of function f of x is a horizontal line, y equals capital L, such that the limit x goes to positive or negative infinity of f of x is equal to L. That's it. So the first case that we had, right, out of the three cases, the three possibilities you can get as the answer, if you have a finite number, it is going to be horizontal asymptote for that problem. So now, if I go back and I take a look at these cases, we see horizontal asymptote for e to the negative x because the function is falling onto the x-axis without actually crossing it or anything like that, so as it goes to infinity. Here is the inverse tangent. It has two horizontal asymptotes. There is one at negative pi over 2, one at pi over 2, and you see the function creeping up to both of them as it goes to infinity. These two cases, right? The top case has no horizontal asymptote at all, right? But the bottom case does. But see, we didn't go, if you go to negative infinity, you can discover the horizontal asymptote for e to the x, right? If you go to negative, x goes to negative infinity, you spot the asymptote. This one has no horizontal asymptote whatsoever. The limit doesn't exist even, but that's what it is. So now I want to address those problems which you guys forgot the rules for, and we are going to compute limit now to find asymptotes of rational functions. So rational function is polynomial divided by a polynomial, which is, call it p of x divided by q of x. And now you had the rules if the power in the numerator is larger, power in the denominator is larger, and then if they are the same, right? Those were the three rules. But we don't need to memorize that anymore because now we can learn a single rule that will cover all of those cases. And that rule is already there. Just take the limit and be done. So let's just come up with an example. Say you are looking at limit x goes to infinity for x cubed plus 3x squared minus 6 divided by 4x cubed plus 1. So let's say this is your problem and you are checking if there are any horizontal asymptotes. So what do we do? There is a very simple thing that follows all problems, whether you can factor or not. And that is, pick the highest exponent of the problem, in this case x cubed, and divide every single term by it. So we have 5 terms, right? 3 on top and 3 on the bottom, and 2 on the bottom. So divide every single one of these by x cubed. And then work out the algebra. Now, if you want to write that as a sentence, as a rule for rational functions, go ahead, because that's the only thing we are using. So what do we get? Limit x goes to infinity, and now I have 1 plus 3 over x minus 6 over x cubed divided by 4 plus 1 over x cubed. That's what we have. And now we just need to figure out how to compute this. How much is 3 divided by infinity? Infinity is very large. So when you divide 3 by it, what do you get? Yes? Yes, exactly. You get one big fat 0. Now, I can demonstrate that with this piece of paper. See it? Piece of paper. If I divide this piece of paper by 2, you get a half, which is 1 over 2, and it's much smaller than this full piece of paper I had. The more I divide, the larger number I divide by, the result that you get is smaller and smaller and smaller and smaller. So, when you are dividing something valuable, let's say, you would rather get a half than a quarter, right? Because half is more than a quarter. The larger number in denominator, the smaller the cut, the smaller the part you get. So you know how Dark Knight starts.
Yeah.
What happens at the beginning of the movie? Yes. What happens during the bank robbery? Joker kills the last one, right? No, I killed the bus driver, right? I killed the bus driver. What bus driver? Right? So, no, I'm not sorry if you are left out. That's one of the pinnacle things you have to see. So, anyway. So, he gets 100% of the cut. There's no splitting, right? There's no splitting. So the more division you have, the larger the number in denominator, the smaller the whole thing is. So if I divide by 2, then that's half. If I divide by 3, now it's a third and it's a smaller cut. If 4 people are sharing something, then everyone does the fourth. Remember when I talked about the lab briefly and I said the worst thing you can do is to divide, split the work. Because you only learn a quarter of the material. And if you learn a quarter of the material, well, having 38 on the exam just makes sense, right? Because you did 25% of the work, plus some partial credit here and there, right? And you push it up to 38. Yes, right? You should do the whole lab on your own and then collaborate with others, right? So now, what happens if this x is infinity? I'm dividing $3 between infinite amount of people. How much everyone gets? 0, right? They get 0 because, right, you have 300 cents in there. So if you're dividing it by 300 people, everyone would get 1 penny, and that's cool. But if you're dividing it with infinitely many people, everyone gets nothing, right? You experience that when you go to a party and they give you the pizza slices that are like, you know what I'm talking about, right? It's like a spaghetti. It's not pizza at that point. Okay, right? You know what I'm talking about, right? They say double cut or triple cut. Do I look like I can handle that? I can't even grip that. You know what's the way to eat pizza my way? You get a large pie, you fold it in half, and eat it. It's very simple. That's the way to eat. You ever try that? And I'm slow too, so I put mayo on it. I just want to see who the noobs are that I don't want to know. So all of you who said, "Oh," just don't talk to me. Because we can't eat together.
Don't knock it till you try it.
Well, you like anchovies on your pizza?
I don't care.
What about pineapple?
Mayo has to be there. I don't care about the rest. Like, it's not important.
Pineapple.
The mayo will kill it, so I don't worry about it.
I'm saying you put mayo on pizza every single time you eat pizza.
Well, if mayo is available. Like at the event on Sunday, they had hot dogs and burgers and sausage and everything. They didn't have mayo. I had to go buy the damn thing. Can't eat. Well, luckily the shop was closed, so I buy the little one. I have to just carry it. When you're Slav, you have certain rules. Anyway, the rest of you news, whatever. Anyway, so anytime you divide a finite value, 3, 6, 1, 10,000, I don't care, with infinity, you have to get 0. Because you cut it up so much that it just goes away, right? It goes away. So every single one of these guys is going to go to 0, and you're left with 1/4. And problem is done. So that goes to 0, that goes to 0, that goes to 0, and the answer is 1/4. And this is the way you will deal with rational functions. Your job is to find the highest exponent, in this case is x cubed, find the highest exponent and divide everywhere by that highest exponent. And it will give you values. Now, there are certain type of problems that they have in a book, and for whatever reason, you just completely do them wrong. So I have to go hunt down at least one of those in the textbook and do one of those examples too, which would reduce your anxiety with math. So give me an hour, I'll be right with you. Please, no puzzle, please. Sometimes they ask me to pick those things.
Oh, gosh, yeah.
Well, he said I can just pick 3, even though there are 5, and I should be good. I'm kind of scared to test it. Because what if he's wrong? And then I have to do another one.
That's how the algorithm works.
Which section we're in? Chapter 2, right?
2.5.
And 2.5. Thank you very much. So now I'm going to finally get the problem. Okay, we're here. There we go. Let's see. There we go. Now, I'm looking at the different edition of the book, so I'm not going to write the problem number, but you will recognize them because they have these algebraic features. So, we are looking at the limit x goes to infinity of the square root of 16x to the fourth plus 64x squared plus x squared outside of the root divided by 2x squared minus 4. So this is the problem. And what I just talked about is you picking up the highest exponent and dividing everywhere.
Can't you find the square root first?
No, because addition, unfortunately. Yeah, right. So when you look at this problem, the highest exponent you have is x squared. Because the square root of x to the fourth is eventually x squared. So all of these exponents are actually x squared. Now, when you do your division, the x squared will have to be stuffed under the square root, and it will pick up another square and become x to the fourth. Let me just remind you of some algebra here on the side. If you remember the problem from algebra, blah, 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 whatever, you had, let's say, 16x to the fourth y. And you say, oh, square root of 16 is 4, square root of x to the 4 is x squared, and then square root of y. Do we see that, and these two were equal, right? They're equal. So we see that x to the 4 under the square root is the same as x squared outside of the square root. So we can actually say that the square root of x to the fourth is x squared. It's a rule. Also, we know that if you have x to a half, right, that's the square root of x. So you can also say, if I also now have everything to the fourth power, right, you see over here you have square root x to the fourth, and on this side you have x squared, because 4 divided by 2 is 2. So that's all side algebra that tells us that the highest exponent is not x to the fourth, but x squared is the highest exponent, which shows when you combine this one with the square root, it's x squared, and the other two are x squared, so the highest exponent you have in a problem is actually x squared. Okay, so now that we know that, we can go and divide everywhere by x squared. Now, we are going to say limit, I have to space this out. We're going to have our square root of 16x to the 4 plus 64x squared divided by x squared. So I'm making sure you know that this x squared is not yet under the root. And then you have plus x squared over x squared, 2x squared divided by x squared, and finally minus 4 divided by x squared. This is when the x squared is going to get stuffed inside the square root and pick up the exponent of 4. So now, in the next step, we are going to stuff the x squared inside the root, and now you're going to have this tall root, because it has to have fractions underneath now. And you're going to have your 16x to the 4 divided by x to the 4 plus 64 x squared divided by x to the 4, and then you have plus 1 outside of the root, because x squared divided by x squared is 1. And on the bottom, you have 2 minus 4 over x squared. One more step to simplify under the radical as much as you can. So limit x goes to infinity, divided by, and now you have square root of 16 plus 64 over x squared plus 1 divided by 2 minus 4 over x squared. And now we have our situation when you are dividing a finite number by infinity. All of them die. 0, 0. what we have is a square root of 16 plus 1 over 2, which is 5/2. And that's the full problem. So you are going to encounter these on your homework, possibly the lab as well. And now you know the trick. So you are picking the highest exponent and dividing everywhere by that exponent. Good. Well, that's the horizontal asymptote. I can actually now add to this problem and say, since the limit x goes to infinity of f of x is equal to 5/2, there is ha at y equal 5/2. We can do that. That's just an extra because we can. So horizontal asymptote at 5/2. That's 2.5. Y equal 2.5 horizontal line, and the function has to bend as it goes to infinity to meet that asymptote. Not to meet and cross it, but to follow it.
Get close to it.
Yeah, always get close to it. Good. All right. Well, the next application, there is more, right? The first line of our limits at infinity, now we know, gave us horizontal asymptotes. And that was a pre-calculus concept you guys learned. The second one also gives us something you learned in pre-calc. Now, at this point, I'm willing to put like $1,000 on the table, see who can recognize that concept. I know. It's been a year, huh? $1,000 is a lot of cat food. No takers, huh?
That's all you.
I mean, you can spend it in other ways too. Probably you're all working out, like, what would I do with $20 billion? Exactly. No takers, huh? Well, I guess tough luck. Let's go. End behavior of the function. What's end behavior of the function? Well, you have 4 possibilities. Your function can go this way, your function can go that way, your function can go this way, your function can go this way. So those are 4 cases. Each one of these can be explained with limits at infinity that go to infinity. Right? This motion here can be decomposed into motion to the right and motion up. So this motion is the limit as x goes to positive infinity of a function to give you positive infinity as the answer. We have this end behavior on the function e to the x and x squared and countless others. But if I go up to these 2 functions, we see that this side of the function goes up to positive infinity as x shoots to positive infinity. This is called the end behavior. Technically, what is the function doing? Is it going to positive or negative infinity as x goes to positive infinity? This is used also to understand that the population model that you guys learned in pre-calc You're going to relearn it again in Calc 2 and finally ditch it in differential equations. The population model, which is terrible, it says population, depending on time, is initial population e to the kt. That's this graph. I don't care what population you are talking about. Humans, ants, rabbits, bacteria. You're not going to have any of that infinite. Can't. This planet is a finite size. You can't fit infinite anything on a finite surface, all right? So that model, that it's nice and cute for us to, do some math gymnastics, is not going to fly when you actually use the limit and realize that as time goes to infinity, your population goes to infinity. Right? Even though the population weight goes on the planet right now, seems like that's achievable, eventually we're going to hit that, what is called carrying capacity of the planet. At which point, it will not be possible to add more. And it's not going to be pretty. So now, we have the limit, x goes to positive infinity, of f of x to go down to negative infinity, and now follow the pattern and fill the 2 on the left. Both on the left are going to negative infinity. And those are the 4 that are there, which would go either way. So that will be what they call the end behavior of the function. And those are not asymptotes of any kind. They are going in this curved manner, right, going always to the left and up, or going always to the right and up, and so on at the same time. So that's the end behavior of the function. You did have this picture with a little squiggle thing inside as well, dotted, in your textbook in pre-calc, and they did not mention limits. They use the words, right, as the function goes to the right and up, and so on. Now we know with the limit, you have x goes to positive infinity, which is this side. You have x goes to negative infinity, which is this side, and all of that stuff goes that way. Bueno? Well, that's it. Just do the homework, right? Bye.